Okay, so we're going to walk through the process just like we learned the other day. What's the first thing we look for? Yeah, x-intercepts, y-intercepts. Okay, which one do you guys want to try first? Y-intercepts. Okay, so let's plug 0 in for x. So the y-intercept is going to be 2 times 0 minus tan of 0. So 2 times 0 is just 0. Tan of 0, if we recall, now I'm going to pretend that I don't have a unit circle on the wall, and I'm just going to let you guys use it if you need it. So 0 pi is right here. This coordinate is what? Is it 0, 1? 1, 0. Okay. So if we have the coordinate 1, 0, tan is y divided by x. So it's 0 over 1, which is just 0. Okay, so we have 0 minus 0, and so the y-intercept is what? 0, 0. And so what does that actually tell us? The x-intercept is 0, 0 as well.
W-H-Y. Oh wait, no, I get it now.
You're good. You're good. It took a second to sink in, but we got it. Okay. Now, if we look at the way the equation is formed, it is possible there's another x-intercept. Can I solve for that? No, I'm not even going to try. Okay, so that's all I'm going to get for the x-intercept. I'm not worried about anything else because I don't know how to solve for it. And I'm not using a graphing calculator to solve because that defeats the purpose of doing this by hand. Okay, so I'm not finding any more x-intercepts. Yes?
Why are you not?
Because it would require me doing the graph and intersect function of my calculator, and then I would have graphed the function. So I can only, when I do calculator use these days, I have to pretend that I'm only using a 4-function calculator, that it's like, I don't know if you guys have moms that did this, but my mom had like a little calculator she kept in her purse. That your moms did that? Yeah, I love it. Moms are timeless, right? That like literally did just like a few little things, and it was like solar operated, you know, so she had to like put it in the sunlight to make sure she had enough sun power to do it. And it was like just for balancing her checkbook. Did all of our moms do that? Yeah, that's the generation difference, right? My mom uses her cell phone, but my grandma did it. I'm like, your mom and my grandma are possibly in the same generation. So, no, my mom, your grandma. I said it backwards. Yes, okay. So we are not going to find any more x-intercepts because for us to do that, we would have had to take this, set it equal to 0. We would have had to use the graphing function of the calculator, and then we would see the graph. And that would ruin doing this by hand, basically. Okay, but we were able to find the y-intercept, and we were able to find that the y-intercept is actually an x-intercept. And so that gives us 1 point. So let's go ahead and graph that, 0, 0. Marvelous. Okay. So after we get that, what do we typically do next? We typically do the derivative. So I'm going to say y prime equals, and what's my derivative? Secant squared x. Ooh, this is getting fun already. We just went from a tan to a secant squared. How you guys feeling about that? This is a fun problem. This was a good one for us to do together, yeah? Okay, so once we take the derivative, what do we typically do with it? Set it equal to 0, and what's the purpose of that? Critical points. Okay, so I take my derivative, I set it equal to 0, and how can I go about solving this? Yeah, positive too. Yeah. Yep. So I can say, let's add the secant squared x over. Yeah, so I can think of this as secant x squared. So just remembering what that notation means, it means that the whole secant has been squared. And I'm very zoomed out. Let me go ahead and zoom in so you guys can see better. Okay. All right, so what should I do now? Square root both sides. And what happens when I square root? How many answers do I get? 2, because I get a plus minus. You guys didn't know this because I haven't made it for the wall, but not putting a plus minus actually kills a baby horsey. We came up with that in honors math too, that baby horsey is the animal. That's that sticky note right there. So there's 11 tallies, and then in their more recent quiz, they added 8 more. So baby horsies are dying left and right. So you guys need to not add to that today when you square root things. Okay, so we got to save the baby horsies because math 2, we cannot count on them. They kill them and then they applaud. I don't know what's happening. Okay, something is wrong here. Okay. Yes, it's very upsetting. Okay, so if secant is root 2, what is the trig function that we are more used to seeing on the unit circle that is related to secant? Cos. Okay, so root 2 over 1 is secant, so we are used to seeing cos, and what would that look like? 1 over root 2. Again, I'm going to have the plus minus. So secant is root 2 over 1. Cos is just the flipped version of secant. So I just went ahead and flipped it. Now, we don't usually see 1 over root 2. I'm going to fix this off to the side. We don't see 1 over root 2. What do we usually see on the unit circle? Yeah, so we would have seen the rationalized form of that, and I'm just going to show the work real quick to remind you. So the rationalized form is when they took this in pre-calculus, probably, or maybe honors math 3, they multiplied it by root 2 over root 2. And then on the top, you have 1 times root 2 is just root 2. On the bottom, you have root 2 times root 2, which is just 2, because the square root cancels out, or you could say it's the square root of 4, which is just 2. And so what we actually have is we have plus minus root 2 over root 2 equals cos x. Okay, so what we're doing is we're going to look on the unit circle and we're going to see where is cos of x equal to positive root 2 over 2. Where is cos of x equal to negative root 2 over 2? And those places are going to tell us what our x values are, because it's cos of an angle equals root 2 over 2, cos of an angle equals negative root 2 over 2. And those angles are the x values. So look at your unit circle. Where is the x coordinate positive root 2 over 2? Okay, x equals pi fourths. X equals 3 pi fourths. Okay, and then where else? Yeah, so we're picturing, so positive root 2 over 2 is right here. There's the pi fourths. 7 pi fourths is down here. Yeah, I'm going to get to that in a second, okay? And then 3 pi fourths is over here, 3 pi fourths, and 5 pi fourths. Now, Michaela brought up a good point. We have to think about the x values that are on our interval, okay? So our interval is from negative pi halves to positive pi halves. Negative pi halves is quadrant 4, but it's the negative version of the angles. So we can only take the answers that are in quadrants 1 and 4. So that's taking pi fourths and 7 pi fourths, but we have to take the negative version of what's in quadrant 4. Okay? It says negative pi halves to positive pi halves, which is typically, the reason I recognize that is because that's typically how they label tan inverse functions. Is they say, or sine inverse functions, they say that sine inverse, the domain is negative pi halves to pi halves. And so in my head, I related that to my prior knowledge, which is like, oh, that's quadrant 4 and quadrant 1. But it's the negative version of quadrant 4 instead of the regular version that we think of. Mm-hmm. Exactly right. Mm-hmm. Yep. Exactly right. Okay, so when we go and look at this, we're going to say, okay, we have these two x values, but they're basically extraneous values because they are outside of the domain, so we're not going to use either of those. They're outside of the domain of the problem. This one we're going to use, but we're going to use the alternate form of it. We're going to use negative pi fourths. 7 pi fourths is outside of the domain of the problem, but negative pi fourths is coterminal with 7 pi fourths. And that is within the domain of the problem. So we're using that same spot. We're using the 7 pi fourths spot, but we're using the negative version because that is what is within the domain of the problem. Because the domain of the problem says negative pi halves to positive pi halves. Yeah, this could be a good one to put like on a cheat sheet. Again, not that it's going to be on an AP exam, but just that it's a good sample problem of a trig problem. Okay, so now we have our x values, and what are we going to use these x values for? Increasing, decreasing, we're going to use them to make our sign chart. Okay, all right, so let's go ahead and we're going to start our sign chart. So our sign chart is going to begin at negative pi halves and end at positive pi halves. And then it's going to have negative pi fourths on there and positive pi fourths on there. Okay. So we are thinking of this, the place that we are plugging this into is we have the derivative is 2 minus, and it's secant squared, right? That's what we were plugging it into. So secant squared is positive no matter what. So we just have to see if this positive number that's positive no matter what, if that number is bigger than 2 or smaller than 2. That's what we have to figure out. Does that make sense? Got to figure out if it's bigger than 2 or smaller than 2. Okay. So I'm going to picture, I'm going to write this right here. I might end up erasing it. We'll see. Okay. So we've got, I'm going to label this, we got pi halves, pi fourths, negative pi fourths, negative pi halves. Okay. So we have, there's a number right in between here, and what number is that? Anyone know their unit circle? Pi thirds, okay. Oop, I wrote pi halves, I meant pi thirds. And then there's this number right in between here, and that's negative pi thirds, okay. So our pi thirds, our negative pi thirds is what we're going to use here. Our positive pi thirds is what we're going to use there. And then 0 is what I'm going to plug in right here, okay? Now, since we're using secant, that is, it corresponds to cos, and it's the flipped version of cos, okay? So what I'm going to do, and I'm using 0 right here, so I'm going to think what's my x coordinate right here? So I know that pi thirds is right a little bit, up a lot. This is how I think of it, right? A little bit up a lot. Did I get that right? Right 1/2 up root 3 over 2. Okay. This one is right a little bit down a lot. Root 3 over 2. Okay. And then right here at 0, we got the point 1, 0. So there's all the points that I need. Now, since we're talking about secant, we are not using 1 over 2. We're going to use 2 over 1. We're going to do the flipped version. Okay. All right. So for root 3, we have 2 minus secant squared. So secant is 2 over 1. For both of them, it's 2 over 1. Okay? So it's 2 minus 2 over 1 squared. So it's going to be negative 2. Okay, so I'm going to write this really small. 2 minus 2 squared. 2 minus 2 squared. Okay? How do we feel about that? Now, is this a typical problem? No, because they're not typically trig. You notice all the rest of them are sine and cos. So we are working on one of the more difficult problems right now, okay? Because we know when we do the derivative of sine and cos, the derivative of sine and cos is sine and cos, and then that derivative is still sine and cos. So we are working outside of our comfort zone right now. I mean, trig in general is outside of our comfort zone, but we are extra outside of our comfort zone right now, okay? All right, so 2 minus 4 is negative. Okay. Are we okay? All right. For this one, we have our x-coordinate is 1. What happens when you flip 1? It's still 1. So we have 2 minus 1 squared. And what do we get for that? Positive. Yep, that's 1. That's positive. Okay. Yes. Yeah, it's a 3, but I wrote a 2 first, and then I tried to make it into a 3, and I was like, it's small. It looks right. Yeah, maybe let me fix that. There we go. More legible now. Okay. So based off this, what is our conclusion? Okay. And where else? Oops. Okay. And it's increasing. Okay. And then we have a negative slant to a positive slant. And so what is that? Okay, relative min. And the relative min has an x-coordinate of, okay. And then we have an increasing slant to a decreasing. Okay. And so the relative max has an x-coordinate of, okay. All right. So let's figure out as much of this by hand as we can. Okay, so relative min, relative max. So I'm going to go ahead and take the function and plug these in, or figure out where to plug these in. If I want the y coordinate of the min and the max, how do I find the y coordinate? Plug it in where? To the original function. So the derivative is going to give me increasing and decreasing intervals. The original function is going to give me y coordinates. Okay, so I'm going to take the original function, I'm going to plug in negative pi fourths. 2 times negative pi fourths minus tan of negative pi fourths. Take the original function, plug in pi fourths. 2 of pi fourths minus tan of pi fourths. I'm going to keep picturing my unit circle. So at pi fourths, what's my x coordinate? What's my y coordinate? Okay. You guys are doing a good job. You haven't even like looked over your shoulder to see that unit circle I put up. Is it because I made it nice and convenient by putting it behind you? Okay. So what is tan of positive pi fourths? 1. Okay. So this is 1. What is tan of negative pi fourths? Negative 1. Okay. So here, when we simplify this, we have 2 times negative pi fourths. Negative pi halves. And minus minus plus 1. Okay? And then over here, we have a 2 times pi fourths, pi halves. Okay? Minus 1. Couldn't rewrite what? The 1 is 2 over 2. You could do that. So we could get an approximate decimal in our heads from this. I'm going to go ahead and write this down. do you mean solve it? Oh, I made it so this is pretty, so when I gave you guys these, I made it so the x coordinate we could graph. And then the y coordinate is all we need to know the decimal for. Does anyone know off the top of their head the decimal for pi halves? Has anyone done that? Ellery's like, I'll figure it out. Grabs her cell phone. I think it's 1.57. Is that right? Yes. I've done it enough times that I now have it memorized. Okay, so we have negative 1.57 plus 1. So negative 1.57 plus 1 is what? Negative 0.57, right? You could. It would just be negative pi plus 2 over 2. Well, these are not like terms because one has a pi, one doesn't. Even if you added them together, you can't like mush them together more than, you're still gonna have two things, yeah. Pi over 2, so 1.57 minus 1 is 0.57. Okay. So we got points. Whew. Okay, I don't know about you guys, but my brain is tired from that. Are your brains tired from that? Whew. Okay. All right, so let's go ahead and put boxes around the things that we are keeping and graphing. So we got our x and our y coordinates, or our x and our y intercepts, and then we've got all the increasing, decreasing, relative maxes and mins. That's all good stuff. We need all that stuff. Okay. So now that we've got that, what should we be doing next? Second derivative. Oh my gosh. So fun. Okay. Our second derivative. So if we're looking at our first derivative, I'm going to look at it in this format right here because that's going to remind me that I need to do the chain rule. Okay, so this format is a little bit more helpful. So thinking of it as secant of x then squared is better than thinking of it as secant squared x. Okay, so if I have y prime is this, I'm just going to go ahead and write this down. Y prime is 2 minus secant x squared. Then y double prime is, what do I have? Yeah, so this derivative of this is 0, so we don't even have to worry about that. So let's go ahead and just do the derivative of this. Oh, well that's fun. Okay, now I am not going to combine like terms, okay? Because when I set this equal to 0, I'm going to think of this as a factor, right? And I know it's kind of strange, but think of it as like you had like an x plus 1, x minus 2, x plus 5. And you're going to set each of these factors equal to 0. Set each of the factors equal to 0 when you solve, okay? So we don't need to put these together and think of it as a secant squared because I'm going to think of it as like this is factored form. All right? Sound good? Okay. So I'm going to take my second derivative. I'm going to set it equal to 0. And I'm going to say I basically have three factors. Negative 2 secant x equals 0, secant x equals 0, tan x equals 0. Does that make sense? Okay. Now, here we have to think of the unit circle. We know that there are places where cos equals 0 on the unit circle, right? So if you think about those places where cos equals 0, then that would be the fraction 0 over 1. Does that make sense? So, sorry, my neurologist is calling me, but it's not my neurologist. It's a recording saying, hey, you have appointments next week. And I'm like, yeah, I know, I got it. I just made them. All right, so if cos equals 0, That means that secant doesn't equal 0, it equals 1 over 0. Because cos and secant are flipped versions of each other. So think of whole numbers, right? So if we think of 0 as a whole number, that means it's 0 over 1. It's not 0 over 0 because that's undefined. It's 0 over 1. Does that make sense? So that means that secant would be taking that 0 over 1 and flipping it 1 over 0. So any place where cos equaled 0, secant does not equal 0. What does secant equal? Undefined. There's no place where secant equals 0. Secant does not equal 0, it equals undefined. Okay, so this is going to be no solution, no solution. So this is, for both of these, not possible. Okay, cos can equal 0, secant cannot. Okay, the only way that secant could equal 0 is if cos at some point was undefined. If cos had a 1 divided by 0 somewhere on the unit circle, then that 1 divided by 0 somewhere on the unit circle could flip to be a 0 over 1 for secant. Is there any place where you've ever heard of a cos being undefined? No. Not on the unit circle. Okay. All right, so then we have to think about where is tan undefined on the unit circle? Or not undefined. Where is tan 0 on the unit circle? We already discussed it today, right? 0 over 1, which is at 0. Okay, so we're going to say this is at x equals 0. Okay, so what happens at 0 and pi and 2 pi, if you want to write that down, you can, 0 and pi and 2 pi. But because of our domain for this problem, the only one we can use is 0. So the reason that 0 and 2 pi are answers is because both of those are 0 divided by 1. The reason that pi is an answer is because that is 0 divided by negative 1. We can only use 0 because 0 is the only answer that is between negative pi halves and positive pi halves. Okay, are we comfortable with that? We're good with that? Okay, so let's go ahead and make our sign chart. We got negative pi halves, positive pi halves. We got 0 right in the middle. We use negative pi halves and positive pi halves because they are the domain. So they're the endpoints of the domain. And so instead of going from negative infinity to positive infinity, like if they said our domain is all real numbers, that's what we would do. But here they gave us endpoints, and so we're always going to use those endpoints when we make our sign chart. Okay. So now when I plug numbers into my sign chart, I'm going to go ahead and use the simplified version now. So I'll say negative 2 times a secant squared times a tan. So I know that that negative 2 is always contributing a negative answer. I know that secant squared is a square number, and square numbers are always positive. So I know this is always contributing a negative, this is always contributing a positive. Does that make sense? So all that I care about is whatever I plug into tan, is that answer negative or is that answer positive? Does that make sense? Okay, so what is an angle measurement that is in between negative pi halves and 0? Negative pi fourths, okay, and then positive pi fourths. Okay, so if we go back to our unit circle over here, we already said that tangent of pi fourths was 1, and we said tangent of negative pi fourths was negative 1. Okay, so tangent of negative pi fourths, so I'm going to say negative 2. Secant squared is always positive, and then tangent of negative pi fourths is negative 1. So see how I'm not ignoring my signs, I'm still using all of them, but I'm not really worried about plugging a number in here because I know what the sign is going to be. It's something squared, it's going to be positive, so I don't care what the number is. I know it's going to be positive because it's something squared. So negative 2, whatever the number is squared, that's going to have to be positive, and then tangent of negative pi fourths has to be negative 1. Okay, so negative, positive, negative, what does that end up being? Liliana with the comic relief, take a bow, Liliana. All right, next one we got -2. Then we got positive for the secant squared. And then with the tan of pi fourths, we got a +1. Liliana, what's this one? Negative. Okay. And so what is our conclusion based on this? Concave, concave up. -pi/2 to 0. Concave down. 0 to pi/2. Is there a point of inflection? Yes. Point of inflection has an x-coordinate of 0. We already know the y-coordinate. What is it? 0. Okay. All right. So let's go ahead and get started graphing some of this stuff. You guys ready to graph some of this stuff? Okay. Since our other points had an x-coordinate of pi fourths, we do need to know where pi fourths is on that x-axis. So if pi halves is 6 boxes, then how many boxes would be pi fourths? 3 boxes. So I'm going to go over 3 boxes and label my pi fourths. Okay, so I got my 0, 0. I've got negative pi fourths, negative 0.57. That's about right. You guys think that's about right? That looks about right to me. Okay, now the tricky thing here is I can see it says it's increasing from negative pi fourths to positive pi fourths. I'm not going to do the concavity yet. I know this is increasing. Decreasing to negative pi halves, but I don't know the y-coordinate. So I don't know if it's like decreasing like this or decreasing like this. You know what I'm saying? Like I don't know like where to go with that. So what I want to do is just maybe find out something about the pi halves if I can. So let's try and maybe just plug in pi halves if we can. We just want to try to find a little bit more information if it's possible. So let's go ahead and take the original function and just plug in pi halves and see what we get. So I'm going to do y of pi halves equals 2 times pi halves minus tan of pi halves. And then what do you guys notice about tan of pi halves? Yeah, it's undefined. Okay. So if you get something undefined, what does that mean that we're going to graph right there? An asymptote. Okay, is that going to also happen for negative pi halves? So here we're going to get negative pi minus undefined. Okay, so I'm going to add this because remember asymptotes were another thing we wanted to find. In the very beginning, if we had a rational function, we would have known, yeah, I should look for asymptotes right away. And this is something that I should have made us look for, but I didn't really think about. So vertical asymptote at x equals pi halves, x equals negative pi halves. And that would be something to look out for on a tangent graph, on a cotangent graph, on a secant graph, and on a cosecant graph. Looking for those vertical tangents because of the interaction for the tangent and cotangent of having zeros and ones that you're dividing, and then for secant and cosecant because you have a zero that's been flipped. So looking for those vertical asymptotes. Okay, all right, so let's go ahead and draw in the vertical asymptote. That does kind of help us, believe it or not, because the vertical asymptote tells us a little bit about how this would act. Okay. All right, so we've got an increasing there. How can we use the concavity to help us draw this? It's got the bowl shape. So I know this is increasing right here. How can I use my concavity to help me? It would start at the top. Okay. Concave up. So we're going to draw something like this. Concave up. I botched that a little bit. Oop. There we go. Okay, does that make sense for our graph? Decreasing into increasing. I've got my concave up. I got my asymptote. Does that fit? Yeah? Okay. And then what should I do? Concave down. Sugar.
Adios, Daniel. No reaction.
He has to say bye, Joshton. All right. So we just did the worst one. You guys survived it.
My brain is gone.
But I really explained every step. How comfortable do you feel with that problem? It was the worst. It was the worst. But we did truly just do the worst problem. So what I would say is now go back and do problem number 1, and you're gonna feel like, ooh, this is not bad at all, because we just did the worst. Yes. Yes. All right, go ahead and get started.